Hello and welcome to our discussion of Module 5 in Big Data Technologies. Going ahead and moving through the various modules, then we'll circle back and talk about them more as needed. So jumping into what is Module 5 about, and it's around solving problems using Spark and Scala and the various other languages that Spark can use. So at the end of this, you'll be able to talk about data frames. And how you use them in Spark, the concepts of parallel programming, and then talk about the concepts of a resilient distributed data set. That's a copy from the course. It's a data set. RDDs are resilient distributed data sets. It's the thing that makes Spark work for both existing and external sources. So talking about Spark to solve problems, why use it and what is it? It's basically Spark makes it really easy to solve distributed parallel programming and problems. The basic idea is that you're able to write a program without necessarily any knowledge of distributed processing and programming that is able to be distributed across a cluster processing large amounts of data that can scale horizontally rather than vertically. What that means is you continue to add additional nodes to the cluster, increase the degree of parallelism of the data, so that you can process workloads that are pretty much unbounded. The things that you use it for includes analytics and machine learning, data wrangling, data processing. You can also do things like graph processing, and pretty much anything that has something to do with big data. These are all uses of Spark. So when we talk about Spark, what is it? And the best way to think of it is there's several different layers of the API. So that at the bottom level, the most primitive and probably, frankly, the hardest to use are things like RDDs, distributed variables, and that's your low-level APIs. Anymore, you don't necessarily really need to use RDDs. Instead, the current recommendation is to go to data frames up in that structured APIs level. As well, you can use data sets, though data sets are somewhat restricted, and you only really need them if there's something that you only can do with a data set. Generally speaking, you're best off using data frames. Data frames provide an opportunity for the optimization engine, the catalyst engine, to determine the best way to do things. There's also SQL is exposed to you as well. And then some additional sort of kind of libraries on top of all that is structured streaming, which is a way of doing streaming since I think version 2 of Spark. You have some advanced analytics and machine learning capabilities inside of MLlib. And there's additional libraries available for you as far as the Spark stuff goes as well. A whole ecosystem of tools, libraries, extensions to make it capable to do more workloads. So talking about RDD. And the basic idea here is it's around dividing things up into a logical partition so that it can be processed on a different cluster, different node in a cluster. So you basically have a series of things that you want to perform that's going to be constructed inside of a directed acyclic graph. So those are the operations that need to be done that are inferred from the code that you write. That's spread across the cluster. And the idea being that the RDDs enable you to have essentially resilience so that if for some reason one of the nodes in the cluster goes down, another node can pick up the work that it had previously done because it knows it was working on a certain amount of data that isn't stored in the cluster necessarily, but it knows that it was working on what partition of the data it was working on and what were the instructions it needed to do on that data. So it can then pick back up from where the one that went away died and redo the work that had been needs to be done. And the basic idea here is to recompute the values whenever an RDD has something bad happen. So whenever you need to do it. RDDs are immutable. What that means, and data frames are the same way, is you don't change them. You create a new one. So it's a transformational, almost functional programming approach to things to where you basically, even if you say something like df, which is what we often use for a data frame, df equals df dot something, you're assigning it the same name, but you're actually constructing a new data frame or an underlying RDD in the process. You're not actually changing any of the data frames or the RDDs. You're just simply augmenting them and creating a new one as a result. You can also do external data sets so that you can pretty much anything that can be supported by either Hadoop or pretty much at this point any sort of big data technology can be accessible. Generally speaking, you don't really need to use RDDs because they are such a low-level construct. The times that you'll need to use them are very limited, though you can. Data frames are typically the preferred approach. So data frame is probably the most common thing that somebody will use if they're writing code. And it looks very much like what you see on the screen. So you do something like a CSV file out there is read into a data frame, and then you might extract something from it, such as take 3 records. So the example you're seeing here is saying read from data slash flight data slash CSV 2015-summary.csv. So that's the file name. We're going to read that. We're going to apply to it a couple things that say infer the schema, and there is a header. So it means the first row contains the names of the columns as well. You should take a look at the values. Spark will take a look at the values after that first row, since there is a header, and try to figure out the data types of each one of the columns. The take 3 does what the name implies. It returns back an array of 3 items. A data set is, like I mentioned, it's only going to work with Java and Scala. Those are basically JVM, Java Virtual Machine constructs. It, generally speaking, will not perform as well as a data frame because data frames have the ability to be optimized to a higher level, caching involved, and a few other fancy things as well. You only really need to use a data set if for some reason you can't do whatever it is you're trying to do in a data frame. So it's the same concept of RDDs. You only go to them if you have to. So some keywords and concepts, and it's a subtlety, but it's important to understand. Concurrent programming is essentially what us old folks would call multi-threaded programming, right? It's the concept that things are occurring at the same point in time, but generally speaking on the same computer. So we do that typically through the use of threads or something similar to a thread, which is a path of execution inside of a process. You may even have multiple processes running on the same computer that is essentially doing something similar to what we now call parallel programming. Parallel programming is essentially, you can think of it as potentially concurrent programming that is distributed. So it is distributed across potentially a cluster of machines, literally processing at the same point in time. It's been around for quite a while. So around the 80s or so, but it was hard. And because it was hard, we stopped doing it so much. It was very challenging, even with multi-threaded programming, to ensure that there were no potential for things to get into a conflicting state to where either you had race conditions where 2 things were trying to update the value at the same time, or you had deadlock conditions where somebody needed something that somebody else has had and they wouldn't let it go until they get something else that somebody else had, and so that you ended up waiting forever. Parallel programming typically parallel distributed programming relies on some sort of a framework, be it MapReduce in Hadoop or Spark, because it's basically making it easier for you to write code without having to go into the low-level constructs. In order to do big data processing, you have to do distributed parallel processing. It's just a factor of we can't make our computers big enough to do the type of workloads that are necessary to handle the volume and velocity and variety of data that we see inside of big data environments. So why did we start doing parallel programming and distributed parallel programming? There's lots of different factors that kind of tie into it. You have solid state drives, which are incredibly fast and last for quite a while, less likely to fail because they're not necessarily moving. And so on. So they made it such that you could create a cluster with really fast hard drives, making it to where the difference between caching something to memory and caching it to a disk is marginal. At the same time, we started having multi-core processors become very popular, and beyond multi-core, you also have this concept of the hyper-threading. So you actually have virtual processors and a physical core taking advantage of something being idle for some small amount of time to basically get twice as much done. We saw incredible improvement in performance of I/O. So input and output has gotten much better, as have networks. We've also got these algorithms now that make it to where it's much easier to write a distributed parallel program. That's things like Spark and MapReduce. Whenever you did things the old way, it was really hard to get it right. You had to spend a lot of time both figuring out how to communicate, how to determine what sections of a program could be executed in concurrently, what sections had to be done sequentially, and it was just a very difficult sort of process. Various types of languages were attempted to be created to solve the problem. What we really needed, though, was something where you basically said what needed to be done and left it to something else to figure out how it should be done. And that's where you also have these environments now where you have Hadoop as essentially an ecosystem and the various type of cloud environments that allow these programs and frameworks to execute. So now for a demo, what I'll do is kind of go through the process that I did at one point, and we'll do a little bit of a cooking show sort of thing. But let me shift over here into this is Databricks, and I should still have a cluster running. No, I don't, so I have to start it up. So I'll go ahead and start that while I go and talk about this. So there's a data set out here that is the data set of consumer complaints by data.gov. This is pretty much if you complain about, be it a credit score or whatever it might be, it is where you would go. And you can download it in a couple different ways. I've learned, though, that the CSV is not necessarily the best way to go because there are various flavors of CSVs and almost no one creates them correctly. The biggest problem you have is if the text inside of a CSV has commas in it. If they're not properly escaped and handled properly on the decoding side of things, then bad things happen. So instead what we'll do is get a link here to the JSON. I'll just go ahead and copy the link rather than downloading it, because you can see it goes to files.consumerfinance.gov ccdb/complaints.json.zip. But I don't want to download it to my computer. I want to put it onto a Databricks machine. And so what we're doing is, it looks like it's up and running. So Databricks has the ability to spawn what looks like a terminal. So I'll make this a little bigger, but we're actually on that computer that I just spun up. So what I'm going to do is go back to the root, and then I'm going to a DBFS, that's for Databricks File System. And the Databricks File System, unlike HDFS, is nothing more complicated than a folder off of a given machine. It's a little more than that because this is actually HDFS is most likely backed by essentially a container, a blob container. But so inside of here, we can go into File Store. That's where things typically get uploaded. So if inside of Databricks you go onto the home page and drop a file up here, or click on the click to browse to upload a file, they end up inside of File Store, which is where I'm at on this window. And then in particular underneath of tables. So inside of here is where files get dropped. And you can see I've got a complaints.json here. The way I got that here was I did a wget, and I'm going to do a -nc for no clobber, and then paste in that URL. And so what that does, and it's not going to do anything because it's already here, is if it's not there, it creates the file, complaints.json.zip. The next thing I had to do was do a pip install unzip because I wanted to be able to unzip it. Since it's already here, we don't really need to install it. And then all I did next was unzip and then complaints .json.zip, and it created the file complaints.json. And what is that file? It's literally a JSON file, and I'm just looking at the first little bit of it, and you can see it's basically a list of arrays is what we've got here. So a list of structures, name value pairs. So once I've got that JSON file, I can then go and load it up. So a little bit of cooking show going on here, right? So I've done some things ahead of time. But what I'm doing here is I'm doing a spark.read.json. And it's actually pretty smart. It goes and it's doing a certain amount of schema inference, a certain amount of structural inference, and basically also validation that things actually came in. So it's going through and distributing that across a cluster. And basically slicing up portions of that file across a cluster, or at least trying to. So we're done with the looking at the actual file. But one of the things you can do is pop open a window onto the actual cluster that we're running, and you can go in here and get live metrics, so we can actually see what's been going on our computer, so our server, so to speak. And you can see we actually are spreading some stuff across. I've got a total of 4 nodes. One of those is the driver. 3 of them are workers. And you can see I'm actually doing a certain amount of work across those. So your next step might be to, take a look at it, right? And if you do a display, it'll display a certain amount of records. It's not going to show all of them. In this case, it's showing roughly the first 1,000. Some of them are filtering out. And you can take a look here and see kind of the nature of some of these tables. So you can see that there's a complaint ID, a company response, what happened, and somebody is basically saying that they contacted a particular company about a particular type of problem, if consent was provided or not, whenever it was received, when there was a response. It's a type of product that's involved, and so on. So pretty interesting information. Not everything has a zip code, and some of them are kind of to preserve the identity of the individual, abstracted out, because sometimes there aren't that many people in a given zip code. So the next thing that we might want to do is create a temporary view. So I'm creating something called complaints, and what that does is create something that looks a lot like a table. So here I can say, give me back the records where state is not equal to 2 characters, basically. So is there anything out here that has a state that isn't 2 characters? Because that might be an indication that it wasn't well formed. And briefly looking at that, yeah, there's a little bit here of minor outlying islands, but most of them look like they're empty, and not equal. Let's see, try an empty string just to see if that'll do it. And you notice there I'm switched over and I'm just writing some SQL. That SQL is getting turned into essentially code that's being sent off to the cluster to do some processing. While that's running, we can actually go in and tell the UI here we'd like to see some fresh data to see who's doing what as far as the nodes go. And the reason you do that is you want to see sometimes if it's distributing well or not. And so now we can see if we have something other. It looks like it's all outlying minor islands at this point. So you might then want to do something like, and you could do this in Scala as well, but oftentimes it's easier to just go to our good friend SQL. And what I'm doing here is show me the counts by state and order them in a descending fashion so we can see which state has the most complaints. And again, if you're curious of what your cluster is doing, you go and you get some fresh data and take a look and see if it's actually doing a whole lot. The differing shades, the darker it is, the more it's working. At the point it starts turning shades of red, it's actually getting pretty busy. This particular one is simple enough that it's not having to do a whole lot, right? So we can see that California has the most complaints, and you might be wondering, well, a more basic thing that we probably would have done is how many records are there in this table, so to speak, or this file, and a count of them. And if I remember right, it's well over 1 million. So there's quite a few. And when we're doing this, it's actually taking that job, spreading it across the cluster, telling various ones of the nodes what to do. So we've got 2.3 mil. You can actually see what it did by taking a look there, or you can actually go into the Spark UI and actually take a look and see exactly what happened by clicking on one of these jobs. And you can actually kind of get a sense of what visualization it was doing. You can get into how long things took to run. It looks like this is probably the one we actually care about because it took like 10 seconds. You can expand expand things out and see exactly what it's doing, and so on. And so this is part of what you end up doing to see if for some reason a job is taking too long, of why it's taking too long. You can also go in and take a look and see exactly how long things are taking, and exactly what the query plan is being done, how much data is being read. We're doing 2 gigs here, and the number of records that went out, 2.3 mil. How long it took to do the various stages along the way, and in this case we were doing nothing more complex than essentially a count, right? So pretty interesting. You may also want to do other sort of queries off of this kind of stuff, which is things like you may want to see what is it by product is one of the things we might care about. So which one of these products have the most problems? And order by count descending. And again, it's going out and basically slicing and dicing this data for us under the covers. The key thing to understand with things like Spark is the language that you choose to do your querying or your operations in really doesn't matter, because what's going on is it's actually getting compiled into that DAG that we've talked about before. So the instructions that are being done, and we can actually see the DAG if we're really interested of exactly what it's doing, and so on. So that one, I think. So you can actually see here's the visualization of the DAG, right? So doesn't really matter if you wrote your commands in SQL to produce that DAG, or Scala or Python. The pretty much if the rule of thumb would be is if your performance matters on the language you're using inside of a construct like Spark, you're not using Spark correctly. Because it shouldn't really matter much. Now, there are some subtleties here and there, but as a general rule, it doesn't, because you're not really running the code. You're compiling the code, parsing it, turning it into something else, and then running that output instead. So you can see here that credit reporting, credit repair, and personal consumer reports is by far the largest source of counts. And you can also do visualizations of that data as well, which is quite compelling from a simplistic perspective. So you can take a look at it and determine visually that, and you can see there quite clearly that the credit-related products are by far the most prominent source of challenges with these sort of tools. So taking a look a little further, that's simplistically the stuff that you can do inside of it. Take a brief moment here to run through another sort of interesting tool that's available to you inside of Databricks as a data scientist. Not just about big data, but it's big data potentially doing some interesting things. There's some different interfaces that are available to you inside of Databricks. These are relatively recent, and by relatively recent I mean less than a month or two, sort of things that are showing up. Inside of it includes this SQL interface. SQL Analytics is something that Databricks is launching as a way of essentially offering a relatively low-cost way of doing read-only operations against data that happens to be housed inside of either a data lake, a blob, or whatever, something that Spark knows how to get access to. And the way it works is there's this concept of an endpoint, and an endpoint is really basically the same thing as a cluster, like we looked at a moment ago. So inside of the traditional interface, you have these clusters, and clusters are either running or they're not. You configure them by specifying literally. I go into it like bigger and I say I want it to be so many workers of a particular version of the type of hardware that it's running on, running a particular version of the Databricks runtime. So it's a pretty intensive sort of thing that a person has to know how to do. You can also do some advanced stuff like passing in some Spark configuration values and setting up lots of other stuff, right? So what you get with the SQL endpoints is a whole lot of a simpler sort of construct. You basically have a generic concept of a size. So it's t-shirt sizing basically, and you say that you want it to be 2x small, and that corresponds to a certain amount of cost for Databricks units per hour. So it's a relatively expensive thing, but not really. You can also do things like auto scaling or load balancing so that it'll spin up multiple clusters and share the load across. And it's also got this photon switch that you can turn on and off, which is, Photon is nothing more than a C# implementation of Spark, and it was written for performance reasons, and it runs considerably faster than Spark. So we're basically starting up this SQL Analytics endpoint, but the point of that is so that I can come in and create queries and query my data directly. So one of the things that it does once the endpoint's up and running, we'll be able to see the databases that are available to us and the tables that are inside of those databases, and you can actually run queries in a very interactive sort of way. These are read-only queries. It's not something where you can do some sort of updates or changes to the data. It's simply pretty much going to be a select, right? And it's also got some nice kind of it gives you an IntelliSense sort of thing, so it hinting as to what it is that you might be trying to write. You can hit tab after you've done enough of it, and we may say star and then from, and we want default, but we don't have the ability to see what's inside of default just yet because the endpoint's not up. But once it's up, we'll be able to basically do hinting of it as well. What this brings to the table from a big data perspective is the ability for somebody that just knows how to do SQL to be up and running and be productive very quickly in this environment. So you can actually come in as just an analyst that knows how to do SQL and start looking at the data that's housed inside of a data lake or whatever. So you can do pretty advanced analytics using a very pervasive language, SQL. So looks like we're almost up. Go ahead and delete that so I can push the dot here in a moment. And it is loading the various tables that are inside of this. So we can do dot, and you can see it shows the various data that's here. So we'll take a look at our good friend Iris, which we always look at. So all I did was hit Shift Enter. I could have also clicked that run thing, and what it's doing here is going out and actually querying what looks like a table, may or may not actually be, and getting back the result set. So a pretty useful and compelling sort of way to do this. You can also do things like create dashboards. So it's asking me if I want to lose that, that's fine, but you can go through and actually create a dashboard. So currently I don't have one, so I can say create, and this we can say, must I turn off my cat box? Oops. Here. And creates a dashboard, and then you can start doing things like adding a visualization. So looks like I need to pick an endpoint, add a visualization. Just going to do something that I've already got here, edges and verses, and basically add those to the dashboard, and you can just drop something on and quickly get up and running. Text box and so on. Not the most compelling visualization. I'm sure there's a different way to do this, but it's basically just outputting the text into various sort of grids. You can also do various type of filtering based upon who's involved and so on. So that's the analytics sort of stuff. And another interesting point is that this endpoint, if you're interested, is something that is accessible from ODBC or JDBC. So if you go into connection details, you can actually see the JDBC URL that you would use to connect to this from a Java app. Or if you are using it with ODBC, you can actually use this and this and the endpoint path, which is how you pick pretty much what runtime you want to use or what endpoint you want to use. And you'll need to create an access token to secure it, but then basically from an application written in something like .NET or C#, connect to this endpoint and act on it as though it were a database and do queries against it. Again, read-only though, you can't update anything here, but you can use this as a serving layer of sorts inside of your architectures. So that's pretty much the high level of what is Databricks. So talking now about deliverable 5. So again, you guessed it, you're going to be doing some work with Spark to solve problems, and you'll want to use the rubric to know what it is that you're doing. And in particular, you're writing a paper on this assignment, a conference paper. Do follow APA format, and you're going to be doing a definition of Apache Spark. Then you're going to be talking about why Spark works better than MapReduce. So what are the strengths? In what situations is Spark better than MapReduce? And generally speaking, it's going to be better most of the time, especially if you can keep things in memory. So that's a key thing to think about, is what is when do you get that 100 times faster sort of performance, when do you get the 10 times faster performance, and so on. Also then you'll talk about what are the high-level libraries that are available inside of Spark. Make sure that you do a definition of RDD, Spark SQL, Spark Structured Streaming, MLlib, GraphX, what are they? GraphFrames is the newer version of GraphX. GraphFrames wraps GraphX. You can talk about both if you're so inclined. Explain how the various components deal with SQL and structured data, machine learning, stream processing, and graph analytics to solve problems. Hint, GraphFrames and GraphX is about mathematical graph problems, including things like PageRank and shortest path sort of solutions. Include screenshots of your script and your results, along with a detailed explanation of your work. some resources, and your rubric. As always, I'm sure you'll be shooting for the mastery. If you have any questions, let me know. That's what I'm here for. Stay safe, and we'll talk again soon.